It's the next question. After you know how it started, what happened then? And suddenly we now have the technology to do it. We didn't have 50 years ago, didn't have the technology 25 years ago, even when we started this. We had to invent things along the way. So we did that. And here it is.
Well, thank you. We'll be back to you in just a moment. So at the moment, we're going to talk about the way that Webb is a completely new way to explore the universe. So today, the mission releases its first science images and gives wings to the dreams of so many people who worked so hard for so long to make this possible. For everyone on Earth, this is your telescope. This is the largest, most powerful observatory ever put into space. It's the product of thousands of people working for more than 2 decades. This is a mission that's singularly focused on the biggest questions in science. So the following phrase is often used too easily, but today actually does mark the dawn of a new era. Today, the Webb mission is open for scientific business. And this is just the beginning. The best is yet to come. So, John, one of the things you told me about is that you really want to make sure there are some people that get thanked, people that put a huge amount of effort into this.
Absolutely. Our current project manager, Bill Oakes, took the project from a time of trouble when we didn't exactly know how we were going to get this to work, and got it all the way to the end. Here it is working, and it's because of Bill made this worldwide team, 20,000 people around the world were involved in making this thing all work, and Bill has been there every day making sure that it would happen. So other special person is Senator Barbara Mikulski. She saved our telescope, and she saved the telescope before us. She made sure after the Hubble telescope was launched and it was not in focus that we would go up and fix it. She made sure that happened. When the Webb telescope needed more resources, she made sure we could get that. So Barbara, we thank you.
Well, it is such an honor to be with you, Jay. I mean, it's been a pleasure to be working with you through this whole thing. Thank you so much. Congratulations, and go Webb.
Thank you.
So this broadcast, much like every part of this mission, is a partnership. On our journey to explore distant places in space, we've been joined by intrepid travelers from around the globe. We have so many extraordinary collaborators. So let's check in with our partners who will be sharing the stage with us today as we reveal Webb's 5 first science images. From the European Space Agency, I'm joined by Katie Haswell in Darmstadt, Germany. Katie. I see Katie in the background there. Also joining us from the Canadian Space Agency in Montreal, we have Nathalie Willette and Sarah Gallagher. Bonjour. I see Katie in the background there. See the waving too. And so naturally, we're also going to be visiting the nerve center of this mission, the Space Telescope Science Institute on the campus of Johns Hopkins University in Baltimore, Maryland. And there we have Alex Lockwood and Carl Gordon, and they're going to give us updates and more. Good morning. Great. So we'll be back with our international partners shortly, where they'll each reveal one of the new images. But today we're also going to be joined by millions of science fans from around the world. Many are gathered at watch parties just for this event. So here we are really going international. So I'm beginning with Bhopal, India. Do we have a signal from Bhopal? Yes. Excellent. Welcome to NASA. Hello, everybody there. Wonderful to be talking to you today, all the way in India. We'll be back to them later. Yes. Great to wave to you. Hi. Wonderful. And we also have a warm welcome now in Portland, Oregon. So we have the feed from Portland. A bit dark, but I see everybody there. Hello, Portland. They're in an auditorium, I see. Okay, next we're going to go off to Milan, Italy. So afternoon in Italy. Do we have the feed from Italy? I guess we have a screen from Italy. And next we're going to go to Rutland, Vermont. So is this Vermont? Hello, Vermont. Hi, everybody. Nice to see you. Thank you for being part of this today. Okay, going even a little bit further afield, we have Netanya, Israel. Hello. Hello, Israel. Yay. Really nice to see you guys. Okay, just one more for now. I see people like giving me hugs. Okay, we also have Vancouver, Canada. Hey, Vancouver. Hi. All right. Wonderful. Wonderful to have all these people with you. So right across from the campus from me, there's also a huge watch party taking place with members of the Webb team. So the wonderful thing is that they actually are people that have worked on the mission, and they are part of our NASA Funny family. So hello, Webb team. There they are. Yes. A lot of people I recognize there. So it's incredibly important to me personally, and also to all of us at NASA, that the universe belongs to everyone. And we are thrilled to share this day with fans everywhere around the world. We'll say hello to some more later in our broadcast. So now it's time to start the main event. What you'll see over the next hour will be a collection of images newly processed by the Webb science team. Only a tiny handful of experts have seen the images so far, and I can tell you that we have been so excited to unwrap them for everyone. We'll be releasing each image in turn in real time. As soon as you see it on this broadcast, it will be available for download on the internet. On the screen below, you can see a timeline showing where we are in the show and what's coming up next. And by the end of the show, all 5 images will be available to everyone. So hopefully you can tell I'm excited. Okay, so let's do this. Okay, we're going to release the first image right here at NASA Goddard Space Flight Center, Maryland, and we're just outside of Washington, D.C. NASA Goddard is home to the project office of the Webb Telescope, and the observatory portion of the telescope, the mirrors and the science instruments, were integrated and tested here before launch. So for many of us, including myself, seeing Webb come together bit by bit right in front of our eyes was an emotional and very inspiring experience. So it's kind of like a part of us was out there with Webb right now. A million miles away, part of our hopes and dreams are out there. So I'm joined now by Jane Rigby, the operations project scientist for the Webb mission. And she's a familiar face for people who've been following this before. So welcome, Jane.
Hi, Michelle.
Okay, so Jane, you not only get the honor of revealing the first image, but this actually got a little bit of a sneak preview. I understand there was a very select audience who's already seen the image.
Yes, so last night, on behalf of the project, I had the privilege of traveling to the White House with the NASA Administrator Nelson and other senior staff to share our first image with President Biden and Vice President Harris. And it was really fun. Oh my gosh. They really geeked out. We had a closed door session where we got to walk through all the images and just share the excitement. And they were so thrilled and they got the profundity of what we're seeing. And so now let's do it.
Okay, we've got the whole world watching. Are you ready to put the first image up?
Oh, let's do it. Let's do it.
Absolutely. All right, here we go.
Okay. So the first image is a deep field, and it's also a deep field with a cluster. So why don't we walk through this just a little bit? So if we come up and look at this image, first of all, it's really gorgeous, and it's teeming with galaxies. And that's something that has been true for every image we've gotten with Webb. We can't take blank sky. Everywhere we look, there's galaxies everywhere. And so, this image, as we're looking at it, what we're seeing is not just all the galaxies, but there's a cluster here. And so the cluster are all these white kind of ethereal galaxies. We're seeing them as they looked back in time, right? The speed of light is only so fast. And so as we're seeing distant galaxies out in space, we're seeing them as they looked billions of years ago. So these cluster galaxies, the white ones, we're seeing as they looked about the time the sun and the earth formed. And then behind the cluster, we have the gravity of the cluster is distorting and warping our view of what's behind. And so there are these galaxies that look stretched and pulled, kind of like they've been magnified because they've been magnified by the gravity of the cluster, just like Einstein said they would. And it's really, there's so much detail here. We're seeing these galaxies in a way that we've never been able to see before. There's just a sharpness and a clarity we've never had. And so we can look at, if we zoom in on this image, and I encourage you as you grab this image at home, like zoom in, you can really zoom in and play around. There are galaxies here in which you're seeing individual clusters of stars forming, popping up just like popcorn. And then we also see in the background of this image, kind of littered like jewels all over the back of the image are these faint red galaxies. Now, that was what we built the telescope to do. The most distant of those are billions of years. We're seeing as they looked more than 13 billion years ago. And so galaxies like that one right there, this little red guy, you're like, okay, yep, what is that? Well, Webb got spectra to figure out what those galaxies are made of. And this is that one. We're seeing as it looked 13.1 billion years in the past, less than 1 billion years after the Big Bang. And we're seeing the elements of oxygen and hydrogen as well as neon. This is how the oxygen in our bodies was made in stars, in galaxies, and we're seeing that process get started.
Yeah, I want to give this a little bit of context. So this is now the farthest away galaxy that we have this sort of detailed information about.
That we know what it's made of.
We know what
like
it's
that.
made of.
Yes.
And this was not a long exposure for Webb.
No, the previous record holder, right, the Hubble Extreme Deep Field, was 2 weeks of continuous work with Hubble, and it was just imaging. With Webb, we took that image before breakfast. The amazing thing about Webb is the speed at which we can churn out discoveries. So everything that you're going to see here in this broadcast is a week, and we're going to be doing discoveries like this every week.
That is absolutely incredible, James. So thank you so much for joining us. It's been an honor to be working with you. Congratulations on all your hard work.
Thank you. It's so wonderful to see it pay off.
So thank you, and I'll see you later on today, I hope. So
Yes.
enjoy the day.
Thank you.
Right. So from distant galaxies, we now turn our eye to something a bit closer. It's a planet, but not one in our solar system. Remember that Earth and its sibling planets aren't the only show in the universe. When scientists and engineers started developing JWST, the search for exoplanets wasn't even part of the plan. That's changed. Exploring exoplanets is now a major component of the mission and the subject of our second big reveal of the day. I'm going to send it now to our friends Natalie Willette and Sarah Gallagher at the Canadian Space Agency in Montreal. So again, bonjour. I guess we're having a little. We'll go.
Okay, I'm Nicole
Okay.
Cologne, and I'm here to tell you.
Sorry for the brief pause there. We're now going over to Canada. Okay. Yep, we're all ready. Yeah. Okay, I apologize. We're having some trouble with the signal from Canada, but luckily for us, we have an exoplanet expert right here, just in case that happened. So this is Nicole Cologne, and she's an exoplanet scientist at NASA, and we're going to talk about this amazing new result from a very hot planet, I understand about 1,000 light years away.
That's right. The exoplanet is named WASP 96b, and it is this hot, gaseous, giant, puffy planet that it is about 1,000 light years away. So that's why today's release is so exciting, because it teases at what Webb is able to do.
Absolutely. So talk us through what this discovery is and why this is so significant.
Well, this reveal that you're going to see is going to show the first spectrum of an exoplanet as taken from the Webb telescope. And this is exciting because it covers infrared wavelengths of light that we have not had access to before. So we've been able to use other telescopes to explore exoplanet atmospheres in the infrared, but not to this level of detail. And this is just one sliver of data that Webb is providing us using the nearest instrument specifically.
And there's something about infrared that is actually particularly good for the spectrum. So in this case, what we're doing is we're actually going to take the light and break it up into a rainbow and look very, very carefully at how much color is coming in each part of the spectrum. So I believe we have that image, if we can put that up.
Okay, yes, I believe we're revealing the spectrum right here. So we now have our spectrum, and this is exactly what you're seeing. As you just described with spectroscopy, what we did was we observed a transit of an exoplanet. We observed the planet as it passed in front of the star. Now, mind you, this is not a direct image. This is an indirect image. So we've seen the effect of what happens when the planet and its atmosphere passes in front of the star. The starlight filters through the atmosphere, and then you can break that down into wavelengths of light, and you get a bunch of what looks like bumps and wiggles to some people, but it's actually full of information content. So you're actually seeing bumps and wiggles that indicate the presence of water vapor in the atmosphere of this exoplanet.
So we have the spectrum up here. Is there anything you'd like to highlight particularly?
Yeah, absolutely. So we have several features marked here. So I call them features. They're these, what I just referred to as bumps and wiggles. But what you're seeing here is a telltale signature, the chemical fingerprint of water vapor in these atmospheres, in the atmosphere of this specific exoplanet. And the other thing we can tell actually is that there's evidence of clouds and hazes because the water features are not quite as large as we predicted. So we can take that and infer that there are presence of clouds and hazes.
Right. Now, one thing that we really want to make sure people understand is with this particular planet, this is a hot world. It's actually closer to its star than Mercury is to our sun. And so we're not looking at liquid water here. But we're looking instead at sort of steam, water vapor.
Yes, this is an exoplanet. It's about the size of Jupiter, about half the mass of Jupiter. It orbits around a sun-like star, but it does it every about 3.5 days.
Right.
So it's extremely hot, extremely close in, nothing like our solar system planets, but that's okay, because what we're seeing is, again, the first exoplanet data from Webb, and this is just the beginning. We're going to start pushing down to further smaller planets and being able to take measurements just like this with the NIRS instrument that was built by the Canadian Space Agency, but also there's three other science instruments that will add to our knowledge in the infrared, as well as direct imaging modes, along with the transit method. So there's a lot more to come.
I guess one thing we should mention is not only are we going to be looking at planets that are more like the Earth in the future, but we'll also be looking at planets in our own solar system.
Absolutely, yes. We're going to have exciting data from planets in our solar system, from Mars outward, as well as asteroids and comets. So stay tuned for a lot more to come.
Thank you so much, Nicole. Thank you so much for telling us about the spectrum, and I'll be seeing you later on today. So we have 3 more big image reveals, and with that, new and more exciting science. But first, let's take a look back at the journey that brought us to this moment. Celebrations like this one are only possible with years of hard work from a cast of thousands. When a new mission is being built, even the most enthusiastic space fans only get to see dramatic moments in this life cycle, the news and images that come out in updates and press releases. But that doesn't really give you the sense of the huge effort that goes on behind the scenes every day. The plans, schedules, and organization to keep everything moving forward really happens, for the most part, out of people's gaze. Webb started as an idea that took root at NASA Goddard. It grew first into planning teams, research projects, schematics, requirements. Then it began the long journey to become real with the development of new technologies, cutting-edge engineering, and finally fabrication, putting it all together. Let's take a brief look back at the visionary journey to how we all got here today.
So today was the final closeout of the purge.
Okay, guys, I can hear Rupa, but
Pretty emotional moment to be in there and actually, closing it up for the very last time, right? You're the last one to touch this. And so that was the final operation. And once that fitting is closed out, there's no more touching of the vehicle. We're ready for launch.
The James Webb Space Telescope, born from the desires of astronomers, achieved with newly invented technology, is the culmination of 20 years of work. Humanity has unlimited questions about our universe. Engineering a way to investigate them requires enormous creativity.
Webb has been a trade-off between engineering performance, what the astronomers want, risk. In fact, when we started 20 years ago, we were actually looking at an 8-meter telescope.
Developing the most sensitive instruments and testing and more testing.
And so you don't want to build one that's just incrementally better than what you've got. Because if that's the case, you would just observe longer on the telescope that you already got. And so every time NASA builds a new astrophysics mission, a new telescope, it needs to be way more sensitive, way more capable than anything we've ever built before.
We all got together in that conference room and we played real time as the images came down from the spacecraft, the very first diffraction limited images ever obtained with Webb. And what we collectively saw as a group was the highest resolution infrared image taken from space ever.
if you're just joining us, I'm Michelle Thaler at NASA's Goddard Space Flight Center, and you are watching live coverage of the release of the first science images from the James Webb Space Telescope. So it's appropriate now that I send the broadcast to our colleagues and friends at the Space Telescope Science Institute in Baltimore. That's the scientific nerd center of the entire Webb mission. So hello, good morning, Alex. The show is yours.
Hey, Michelle. Welcome to the Space Telescope Science Institute. I'm Alex Lockwood, and I'm here with Carl Gordon, who is an astronomer and one of the key people in delivering the images that you're going to see here today. But actually, before we get into the amazing images, we're going to talk a little bit about where we are. We're standing here outside of the Mission Operations Center, which is the key central hub for Webb. For the past 6 months, scientists and engineers have been working 24/7 since they took control of the telescope 30 minutes after launch to prepare for today and for the amazing science to come. Through all of the major deployments, focusing, aligning the telescope, and calibrating those 4 amazing science instruments, it was all done in this building. And from here on out, we'll have daily communications with the telescope, including sending commands and downloading data with the help of the Deep Space Network. In addition to mission operations, we are also the home of science operations. Well, what does that mean? Every year, we solicit proposals from astronomers across the country and the world for what they would like to look at with Webb. Then we hold a rigorous selection process to select the ideas that will best utilize Webb to study and understand our universe. When the data come down and astronomers analyze their results, we are the lucky ones who get to share that data and those amazing science results with you. And we knew that today was going to be so exciting with the first images, so we've actually been preparing for years. Here is Klaus Pontoppidan, project scientist for Webb and the technical lead for the first images.
Yeah, it's been a year
to tell you about the process of the past few years.
I look back and my first email related to the first images was back from 2016. So back then, a committee was created, and this committee was charged with coming up with a long list of targets for the first images. And the reason for that is that the observatory can't see the entire sky at any given time. And this is because you want to avoid the mirror seeing direct sunlight to keep it cold. And it actually had to be quite a long list. We ended up with about 70 targets, from which we had to select only a handful. You know, what would create the most beautiful images, what would highlight the instruments, the 4 science instruments for Webb, and what would highlight the 4 major science themes for Webb. And it's a celebration as well of the beginning of science observations.
And we knew that selecting the images was just the beginning, that we would need a trained eye to take these exquisite data and pull out the beauty and the science potential. So here's Jody Pasquale and Elisa Pagan to tell you about how they processed these beautiful images. And they have one downstairs. I think they missed some of that beginning.
We're basically translating light that we can't see into light that we can see by applying color like red, green, and blue to the different filters that we have from Webb. And the reason we want to color the images is because there's actually more that you can get, more information that you can get from the image if you see it in color.
So it's a matter of picking and choosing filters and colors that enhance the details and the structure in the image itself.
The shortest wavelengths of infrared light and assign those blue colors, and then move our way down to green and red as we go into longer and longer wavelengths.
And then we additively combine those together to get our full color image.
But there is a lot of aesthetics that are involved in this. Painstakingly going through and cleaning these images up with an attention to detail, a level of detail like at the pixel level in every image.
So when I'm working on the astronomical data, it is this sort of marriage between art and science. When you're choosing colors for the filters, you really are trying to show the different details and the processes that are happening in astronomical images. But at the end of the day, you want it to be very compelling. You want it to be very beautiful because space is beautiful.
And after those images were processed, it was a select few of us, very lucky few of us, who got to see the first images.
It's downscaled so just to make it a little more handy, so it's actually high resolution. So we have a team of about 30 people who are producing these images, and we feel incredibly privileged to be the ones who are the first to see these science-like images. When we saw the first data come down of real targets, people were speechless and there were emotions, because we could see how amazing this observatory will be. The detail, the sharpness, the depth. And when we saw the first color images, we knew that we had a winner.
And now we are ready to see Webb's first image of a star dying, a planetary nebula called the Southern Ring. Let's do it.
Oof.
Wow, wow. This near infrared image is, wow, the detail. Oh. Wow, okay, well, here we are. We have a near infrared image on our left, or on maybe your right. And here on the right, we have a near infrared image. And so I'm here with Carl, our astronomer specialist. Can you tell us what we're looking at in these images?
So this is a planetary nebula. It's caused by a dying star that has expelled a large fraction of its mass over in successive waves.
Okay, so we actually see those waves in these images.
Yes.
Wow, wow. And so there's a lot of structure. Can you tell us a little more detail about what we're looking? Maybe start with this one on the left.
Yeah. So in the NIRCam image, you see this kind of bubbly, almost foamy appearance throughout the whole nebula with some very structured shells. And this foaminess is showing up in orange mainly, and this is due to the molecular hydrogen that's newly formed in the expansion, just lighting up the gas and dust of this nebula. And then as we move inward, you see this kind of very blue haze in the inner region, and this is actually due to very hot ionized gas that emits well in the blue, that's heated by the core, the leftover very hot core of this star.
And what about these like rays that I'm seeing in this image?
Right there. So there's also rays in the outer regions that you can kind of see, and these are holes in the inner nebula that are actually allowing the central star's light to come out and kind of light it up like patchy clouds with the sun shining through.
Wow. Oh yeah, that's what it looks like. That's so cool. So you're actually a mid-infrared astronomer, which is different than near-infrared. And so what can you tell us about the details in this mid-infrared image?
So it looks quite different in color, partly because we're seeing different kinds of physics going on here. So we're actually seeing in the blue, you see a lot of blue. The blue is actually due to hydrocarbon grains that are emitting very strongly in the blue for MIRI. And they show the very similar structures to what we see in orange and NIRCam because the molecular hydrocarbon actually forms on the surface of dust grains. And so again, as we move inward, we see that the inner region is again hot ionized gas, but now it glows red because that's where it emits the strongest for MIRI wavelengths.
Okay.
And then as we go into the center, we see kind of the surprise for us, which is we knew this was a binary star, but we effectively didn't really see much of the actual star that produced the nebula. But now in MIRI, this star glows red because it has dust around it. So in MIRI, we got to see both stars very clearly.
Yeah, you can't see it in the first image really, but there's two stars there. So that's a fun surprise. And I think that there's another little Easter egg you want to tell us about?
Yeah, so this was, the Easter egg is this kind of narrow filament up in the top that's radially aligned. You can kind of see it very clearly in the MIRI image. It shows up as this blue structure, and it points very much to the central sources. So I thought, oh, this must just be a density enhancement in the outer nebula. I thought that very, very strongly, but other people on the team were like, no, it's a background edge on Galaxy. Well, I made a bet that said, no, it's part of the nebula. By the way, I lost the bet because then we looked more carefully at both the NIRCam and MIRI images, and it's very clearly an edge on Galaxy with a dust lane and a bulge. So I lost the bet.
Well, you lost the bet, but you got these gorgeous images. So I think it's a win for everybody. Anything else you'd like to say today?
I can't wait to see where we go from here.
Neither can I. All right. Thanks so much. Back to you, Michelle.
Thank you, Alex and Carl. And I have to say that image is absolutely spectacular. So as you know, people from all over the world are watching us today and joining in our excitement as we release Webb's first science images. We've been checking in with our colleagues in Europe and Canada throughout the program, but we also want to take a moment to include the people at the oh so many viewing parties scattered around the world like stars in the night sky. So let's check in with some of them now. First, we go all the way to Perth, Australia. Do we have a signal from Perth? I guess nothing from Perth right now. Maybe we have some of our other feeds. We're going to check in with them right now. Do we have Winnipeg, Canada? Oh, there it is. There's Australia. There's Perth. Hey, waving to Perth, Australia. Thank you so much for joining us today. And next we're going to Winnipeg, Canada. Hello, Winnipeg. At a planetarium. Everybody's enjoying the show, I hope. Okay, Dayton, Ohio. Everybody's watching on the, there we go, Dayton, Ohio. Hello, everybody, Dayton. Nice to have you here with us. There we go, yes. Hey, hey, Dayton. Hey, they're jumping up and down. Hi. Okay, all the way Bangalore, India. Bangalore. Hello to Bangalore, India. Hey. It's absolutely wonderful. Hey. Okay. So I hope you enjoy the rest of the images we're releasing. Okay, of course, NASA's family extends all over the country. The team at JPL in Pasadena, California, they're on site to celebrate with us. So hello, JPL. Some of my favorite people in the world. Hey, hello. And I think the last place we're going to right now is Northrop Grumman, one of our major contractors. Hello, Northrop Grumman. Oh, hey, all right. Yay. Nice to see you, Northrop Grumman. All right, now there's also a big watch party right here on the NASA Goddard campus. Many of these people have worked on the mission itself, and we also have top NASA leadership and representatives from our government. So hello, hello watch party at Goddard, yay. Okay, wonderful. So, I mean, at NASA, we are so fortunate to have all of these friends and colleagues around the globe. A major partner in the Webb mission is the European Space Agency. ESA contributions have been essential to so many aspects of this project, including Webb's spectacular launch on the Ariane 5 rocket last December. I'm very pleased to turn over the show for a few minutes to Katie Haswell. She's joining me from the European Space Operations Center in Darmstadt, Germany. Hello, Katie. Good afternoon.
Thanks, Michelle. Thank you, Michelle, and welcome to Germany. We're at the European Space Agency.
I'm still getting all kinds of IFB from lots of
center. It's where the teams effectively fly the satellites. They're a little bit of a cross between air traffic controllers and pilots. We have lots of different control rooms here. This is the main control room, and as you can see today, it's not in use, so we've been lucky enough to move in here for today. I have two very special experts with me, both scientists from the European Space Agency. Giovanna Giardino is a near-spec scientist. Giovanna has been working on that for many years and lots to tell us about that. And Mark McCaughrean is a special advisor for space, for science and exploration. These two guys have been working on the Webb Space Telescope for a long time. So we're very grateful to have you with us. Thanks, folks.
Pleasure.
We are excited to reveal our image with you. But before we do that, we thought we'd give you a little bit of background because we've come here today because these guys were the first ones to pick up the signal during the Webb launch, when Webb first launched. They run a system called S-Track, which is NASA's deep space tracking system, and they were listening out when Webb called home. And the controllers here have been looking after a whole very, very impressive list of missions since 1968. ESA has played a very, very important role during the Webb for the Webb Space Telescope. They provided the launch on board the awesome Ariane 5 launch vehicle from the Guiana Space Center. The atmosphere in the Mission Control Center was electric, I can tell you, I was there. They've also provided people. We have 15 ESA scientists working at Space Telescope in Baltimore, and also they have provided the infrared spectrograph, the near-infrared spectrograph, and also half of the MIRI instrument, which is the mid-infrared instrument. Let's take a look at those now.
Webb's 4 scientific instruments include NIRSPEC, the near-infrared spectrograph led by ESA. NIRSPEC splits near-infrared light from astronomical objects into its components. Like a barcode, this will help scientists understand the physics of the objects they're observing, from their temperature to atomic makeup. NearSpec can observe parts of an object or the sky using an image slicer and an array of microscopic shutters. Webb's Integrated Science Instrument Module, located behind the main mirror, also contains MIRI, a mid-infrared camera and spectrograph. Seen here during testing, MIRI's been developed by a partnership between Europe and the US. MIRI detects mid-infrared light from planets, stars, and galaxies. It can analyze molecules to help us deduce what astronomical objects are made of and peer into clouds of gas and dust where stars and planets are born. Together, these instruments will help Webb detect and analyze light from the very dawn of time, revealing the universe as never before.
So let's get ready to reveal our image. And remember that one of Webb's jobs is to find out about galaxies, more about the galaxies, but also to help us to understand how they change. And this image is going to be very, very useful for that. Let's reveal it now. There it is. It's called Stephan's Quintet, and it's wondrous. Giovanna, what are we looking at?
Yes, like it's a quintet. So we are looking at 5 galaxies. Galaxies are this giant structure that, as we've seen, we see everywhere around us in the universe. They contain from million to 100 billions of stars. And in fact, we live in one of them, the Milky Way. And here we see 5 of them. This is a closer galaxy in the foreground. And these 4 are at a distance of about 300 million light years from us. And they're locked in a close interaction, a sort of cosmic dance driven by the gravitational force. You can see here these 2 in a process of merging within each other. This is a very important image and an area to study because it really shows the type of interaction that drives the evolution of galaxy. That's the mechanism of galaxies' growth.
I love this image of the cosmic dance moving through each other. Mark, there's a lot going on though in this image, isn't there?
There is. So this is a near-infrared image and a mid-infrared image combined. And when we zoom in on the left-hand side here, we see this foreground galaxy. We see lots of individual stars in there actually resolved as point sources, which is remarkable. And then as we pan across, we actually see the galaxies in the merging galaxies. We now see gas and dust, which is being heated up in the collision between those galaxies. And that's a place where new stars are being born today. So we're actually seeing the process of creation of new stars in this region. And then when we look in the background here, we see not only the galaxies at 300 million light years, but also stars in our own galaxy. These snowflake structures that you see here, those are nearby stars, but in the corner and around the edges, we see galaxies which are much, much more distant, much further away. So similar in some sense to the ones that we saw earlier on in that deep field. And so this image actually takes us from the nearby galaxy, our own Milky Way, through these galaxies which are evolving today, all the way to the distant universe. And in a way, it captures cosmic evolution of galaxies over those 13.8 billion years.
So we have another image, don't we, that we can
exactly
look at?
So if we strip away the near infrared view there of the stars predominantly, now in the mid infrared with MIRI alone, we see mostly gas and dust. So we see the same galaxies again, the 2 merging, and then we also see something very interesting up at the top here, because this top galaxy has something new and bright in the middle of it. And Giovanna, tell us what that is.
Yeah, that's an active black hole. We cannot see the black hole itself, but we see the material swirling around, being swallowed by these sort of cosmic monsters, and this gas gets heated to extremely high temperature as it falls onto the black hole, and it becomes very bright. In fact, this is outshining the galaxy. Here we see luminosity that are 40 billion times the luminosity of our suns. It's really, really bright. And with NearSpec, we can zoom into this area, and we have this technology that allows us to take thousands of images at different wavelength channels. So see this distribution of the gas, what's going on in the gas in different regions of this core area, and understand the composition of the gas, the velocities, the temperature. So that's very important to understand the physics.
So
of
it's
these
giving us so much information, and it just shows the power of this telescope. Mark, this is just the beginning though, isn't it?
I think that's a very important takeaway from today. You know, these are like pictures just taken over a period of 5 days, and every 5 days we're getting more data, which will contribute more in that direction. It's a culmination of decades of work, but it's just the beginning of decades. And you know what we've seen today with these images is essentially that we're ready now. This telescope is working fantastically well. And you know, to borrow a phrase from a famous rock musician, you know, we're ready to turn this telescope up to 11. It really is time. It's fantastic.
Thank you very much indeed, both of you. Back to you, Michelle.
Thanks, Katie. It is so great to have you and your colleagues with us on this historic day. So before we get to the fifth and final image reveal of the day, it cannot be said enough that an achievement like the James Webb Space Telescope is something bigger than any one of us. It's bigger than any organization, any country. This truly takes a planet. Webb belongs to all of us, and starting today, the discoveries start and they're not going to stop. This is just the beginning. We've said several times throughout the broadcast that the Webb mission is about people, and during the construction of the Great Telescope, people started to see themselves in it, literally. Day after day, people visited the observation window at NASA Goddard, and looking through the glass, they snapped selfies of themselves reflected in the gigantic golden mirror. These photos are actual reflections of the enormous human investment and the emotional commitment that brought this mission to life. And now, years later, that mission is finally collecting light from the earliest days of the universe, all the way to worlds in our own solar system. It's the same mirror that reflected the many faces who see themselves as part of the journey to understand our shared origins. Let's stop for a moment and appreciate the people behind Webb. Okay, it's time now for the last image to be revealed. Here we go. So Amber Strawn is Webb's deputy project scientist. She's here with me today to share the final big reveal of the day. So Amber, it is so good to see you. How are you feeling?
So great, so exciting. What a great day this is.
Yeah, so one of the things that we're going to do is before we get to the final image, the James Webb Space Telescope has taken us all over the universe today. So let's do a quick review of where we've been so far. So Jane Rigby got us rolling today with an extraordinary new deep field image, showing us one of the farthest views of the universe ever.
Yeah, this image really does demonstrate that JWST can do exactly what we've designed it to do.
Yes. And the Canadian Space Agency then took us to the massive planet WASP 96b, where the team has detected evidence of atmospheric water.
And here again, we're seeing the incredible efficiency of this observatory. We're able to do these kind of measurements in a fraction of the time that we're able to before.
And then we zipped up the road from NASA Goddard to the Space Telescope Science Institute, where Alex and Carl showed us the exquisite Southern Ring Nebula, a mixing bowl of stellar matter around a pair of dying stars.
Yeah, and I'm just blown away by the level of detail we can see, like in the outer part of this nebula. It's incredible.
Wow. Okay. After that, it was off to Germany, where the European Space Agency wowed us with pictures of galaxies interacting and mixing together.
Right, and this image, again, it's incredible because it's showing us one of these fundamental processes of the universe, how galaxies merge together, and we're able to learn about these processes in a brand new way.
So the Webb team has a lot to cheer about right now. So across the campus, there's this big watch party, and we can feel the excitement all the way from over here. So let's join that celebration now. We're back with Senior Project Scientist John Mather, along with the head of NASA's Science Mission Directorate, Thomas Zurbuchen. Hello.
So, John, we looked around the world and we're the only ones with a cheerleading crew right over there. That's amazing. Look, you've been with this mission for decades. How do you feel today?
I am so thrilled and so relieved. This was so hard, and it took so long. It's just impossible to convey how hard it really was. That we risked so much to say we're going to go do this, and it's so near impossible, but we did it.
Yeah, there are thousands of ways this can go wrong.
Yes.
Many of them, we worried about and frankly feared even after launch. I have to tell you, I was really, really nervous. And, it's almost like athletics for me. You always get to know the team when they're on the field. And on the field, they were right after this launch, and they were perfect.
They absolutely were. And I really wasn't worried, but maybe I should have been.
Yeah, that's difference between the two of us. I always worry. I always tell everybody I'm paid to worry, frankly, and that's good. What we want to do, though, is, just really thank the team again. Of course, we heard Bill and Scott and Greg talking about the team that is there. I think what's also important is to recognize that Bernie is sitting there. It was the first manager. I was sitting there. Could you stand up? And I want to mention that Phil Sabelhaus, who was a manager also during that time, is no longer with us, but his heart is with us today. Yeah. I have to tell you, John, after each one of these milestones, I called a lot of people. I called Bernie, for example, and I called people at my job and people who are administrators, because there's many of them. And I just wonder how you feel about the team. Just give you the word here.
I am just so thrilled that we had a privilege to assemble such a brilliant team. We drew from the best of the best, and here we are. So my extreme deep thanks go to all the people who built that team, not only to Bernie, who started us and helped us build up all the technology, to Phil, who made sure we would have a plan, and then when we didn't have quite enough money, to Bill, who pulled it all together and made it get all the way to the end. I am so thrilled that we had so much talent to draw on. And here we are, we have the support of the country and the world to take on this immense challenge.
You know what I'm most excited about? There's tens of thousands of scientists, and frankly, some of them just got born or not even born, who are benefiting from this amazing telescope, because it will be with us for decades.
It will be. It took us about 25 years to get here, since 1995, and we have at least 25 to go, I hope.
So look, we are in a sense of these images, the art that is out there in the sky, revealed for the first time. We're thinking of the team and we're thanking them. John, thanks to you, thanks to all of you, and back to Michelle.
Thank you so much, Thomas. And this entire collection continues to just absolutely astound me. Okay, Amber, so here it is. Can you walk us through the final image reveal?
Absolutely. Here we go.
The last image is, wow, look at that. So Amber, can you tell us a bit about what we're seeing here?
Of course. This stunning vista of the cosmic cliffs of the Karina Nebula reveals new details about this vast stellar nursery. Today, for the first time, we're seeing brand new stars that were previously completely hidden from our view.
There's something you want to point out here?
Absolutely. So honestly, it took me a while to even figure out what to call out in this image. There's just so much going on here. It's so beautiful. One thing that really stands out to me is you sort of get this sense of depth and texture from this new data. There's a lot going on. To call out a few specifics, first of all, in general, the Karina Nebula is a nearby star-forming region within our own Milky Way galaxy, about 7,600 light years away. And in this view, we see some great examples, first of all, of hundreds of new stars that we've never seen before. We see examples of bubbles and cavities and jets that are being blown out by these newborn stars. We even see some galaxies sort of lurking in the background up here. We see examples of structures that honestly, we don't even know what they are. Like, what's going on here? The data is just so rich.
And there's something really special about the infrared. Infrared can actually see deeper into these star-forming regions.
Absolutely. That's one of the great things about infrared, is it really does reveal what's going on here in a really cosmic sense. And in general, what's happening in sort of this overall landscape is we have these gigantic, hot, young stars up here to the top of this rim, and the radiation and stellar winds from those stars is sort of pushing down and running into all of this. This is gas and dust. And of course, we know that gas and dust is great raw material for newborn stars and baby planets. But there's a flip side to this story, and also a little bit of a mystery, because these same processes can serve to sort of erode away this material and stop star formation. So we have this sort of delicate balance going on of new stars being formed, but at the same time, the star formation is being halted. And for me, when I see an image like this, I can't help but think about scale. You know, every dot of light we see here is an individual star, not unlike our sun, and many of these likely also have planets. And it just reminds me that, you know, our sun and our planets and ultimately us were formed out of the same kind of stuff that we see here. We humans really are connected to the universe. We're made of the same stuff in this beautiful landscape.
And actually, the Karina Nebula was one of my favorite images from Hubble. So Hubble looked at this as well, right?
Absolutely. Yeah. The Hubble image of this is also spectacular. We saw it in a different kind of light when Hubble took an image of this particular nebula. And then you can see amazing things with Hubble, but when we zoom into this new image, we're able to see so much more detail. And of course, all of us, you know, I grew up on Hubble, and all of us love Hubble. And I'm so excited to see what these two amazing observatories are able to do really in tandem with each other.
Thank you so much. And again, congratulations. It's been a pleasure to be working on this with you. I'm just amazed by what's been going on.
And too. Thank you.
So as we're wrapping up, one of the things that I really have to say is the journey that we've been going on is so very dramatic for me. So we've gone all the way from the birth of stars, and we have all the way from the distant galaxies to the birth of stars. This is where we all began. This was the whole point of the James Webb Space Telescope, to figure out our origins from the very, very early days of the universe to star and planet formation very nearby. So right now, I'm very honored to have our last special guest. This is the administrator of NASA, Bill Nelson. An honor to be with you, sir.
Hey, what a pleasure. What a banner day. It's clear that Webb represents the best of NASA. It maintains our ability to propel us forward for science, for risk-taking, for inspiration. And we don't want to ever stop exploring the heavens, nor stop daring to take another step forward for humanity. In the words of the famous Carl Sagan, somewhere something incredible is waiting to be known. I think those words are becoming reality.
Absolutely.
Thanks, Michelle.
An honor to have you here. Thank you very much. Wow. So this is a celebration for all humanity. If you've ever looked up at the night sky and wonder, whoever you are, wherever you are, this is your telescope. And we also salute the thousands of people who have dedicated part of their lives to making Webb a reality. I also want to give a big shout out for the superb media team who's helped bring Webb's story to the world. This broadcast is a joint effort of the superstar producers, animators, and social media specialists at the Canadian Space Agency, ESA, NASA, and especially the Goddard Space Flight Center. Webb captures light in distant colors that the eye can't see, and you've actually made this visible to the world. So finally, if you go to nasa.gov/web-first-images, you can download all of the images and data we've just shown in full resolution, and check back often. From now on, we share new discoveries, exciting new destinations around the universe. July 12th, 2022 marks a huge day for science. It's only just the beginning. For everyone at CSA, ESA, and NASA, I'm so very pleased you could join us. I'm Michelle Falk. Go Webb.
Yeah, can you, hey, everybody, thank you for coming. We're just kind of getting organized for the next phase here. So Roger and team are going to do some questions for and answers for members of the media. And but I want to thank everybody for coming out. I'm glad you sort of had a chance to get here and see live, like everybody else, the first images from the Webb telescope. I used to tell audiences all the time over the years, is like in the old days, right? Scientists would discover something and they would share it with other scientists and they would argue about it for a while. And there was no internet, so they would send letters across the world to talk to each other, right? Paper goes over there, they comment and send it back. By the time it actually got to a public forum, by the time some sort of scientific discovery actually made it through that whole process, it was put into textbooks. And so the only people that got it were people that were sort of in academic institutions. But today, fast forward to today, this is the latest in science. This is the latest of discoveries, and we're here today. We're all seeing it together in this amazing sort of forum. So that we've come a long way in delivering in science communication. So that's really one of the things that I wanted to reflect on. You are free to leave. We're kind of done with the part of the program that we're going to just show everybody. We are going to kind of do a little kind of question and answer and thing here. You're free to stay, and we'll see where we go from there. Okay, thank you. Anything else? Yeah, so we're just going to get the media in place. I think what we wanted to do is anybody with sort of cameras that want to do something, we're going to center you in the front of the room here between the lights, and we'll kind of go from there.
Well, thank you all. Ready? Thank you all for being here. Hope you can hear me. I'm Rogier Windhorst. I'm a Regents Professor here at ASU. See many familiar faces in the audience, including my daughter Jamie and her family, and many of my team, Rolf, Seth, Jake, Caleb, Tim, Darby, Laundry, and many others that support the project. So this is a new golden age astronomy, a new era of discovery. What you've seen today is the cosmic circle of life, from the beginning of stars to stellar death. Images are just absolutely, literally out of it. Thought Hubble was good at this, but this just blows the mind. Who would have thought 2 years ago when we started that it could be this beautiful? So I'd be happy to take some questions or illuminate some more things. Rick, could you show the screen that's on the workstation here? So we could can answer questions as they come, assuming the internet is cooperative. So today, there's some web speed problems. Obviously, NASA is overloaded. Data taken from the world today, and that will persist for a couple. We were lucky enough to have some of our first web targets, web fields taken in the last few days. We haven't seen the data yet. We were most strictly forbidden to see it until this day because nobody was supposed to release anything early. Of course, they made an exception, President Biden, right? And he took one of the targets from one of the people in my team then code cluster SMAX 073. I want you to let this sink in. If you could click on that cluster, upper left, click on the image and enlarge it. This cluster contains a central galaxy. Let's turn, do you really need lights here? Because okay, good. Yeah. I want you to let this sink in. This galaxy is probably 9 billion years old when it emitted its light. Its first stars were born a few hundred million years after the beginning. We'll get to that. And that light was on its way from a redshift 0.4 when the universe was 40% smaller than it is today, for 4.6 billion years. So the Earth was born when you see this galaxy. Yeah, we're basically an afterthought, cosmic star formation. We came late. These guys were there really early. So I'd be happy to take questions. I don't know how you want to do this, but there is so many new questions and mysteries here that are studied. Very good question. So I hope the audience can hear it. So the question is, how did we identify these targets? So there was an international team that picked, like they did for Hubble when the cameras first started operating in 2009 and before that. And this is an infrared telescope that is especially designed to study the birth and death of stars behind the cosmic dust, all the way from here to almost the beginning of time. So they picked targets where they knew they could optimally show the performance of Webb. And this target, if you could click, if somebody could stay there, click on the blue and brown, the last image you saw, which I call the beachhead of cosmic star formation. We knew that image, the Karina Nebula, would be so absolutely stunning to show where these giant stars formed early, and then their ultraviolet radiation, the aftermath, the supernova explosions, and other stars like the sun expelling their last layer. So, yeah, that one. We knew that this would be a most stunning image to show in the infrared, because now you can see at this beachhead in the front where all these giant stars on top are like, which they are the big ships in the ocean of hydrogen. And their ultraviolet light causes the waves that hits this beach. And on literally the sand and the dust of this beach inside are little canoes, little rowboats that are small stars that are waiting to be formed. But the ultraviolet radiation of the big stars needs to sculpt that away and make it free so that the stars could form. So we thought that this would be one of the best examples to show how stars like stars like the sun would form. And every one of these little dots is a star like the sun that's now being liberated from that beach of dust. Dust will be blown away, and soon it will be a star that develops its own planet. Soon it will shine like the sun. But it's the courtesy of these massive stars at the top that are doing it.
Discuss why it was necessary to develop the Webb telescope and why it was necessary, because everybody again knows Hubble, why it was necessary to move on from Hubble to Webb.
Well, Hubble is an ultraviolet to optical telescope and a little bit in the near infrared, but it's pretty much like the eye, a little bluer, a little redder, but that's it. And most of these, that's where you see the action of atoms in the universe. But if you want to see the action of molecules, you need to go to the longer wavelengths in the infrared, like night vision goggles. The eye cannot see them. Therefore, we had to design the Webb telescope to give it those wavelengths. Yeah, well, Webb started in 1995, shortly after Hubble started functioning properly in 94. And then they decided, well, because we know these things take 20 years from beginning to end. Let's plan for a sequel. And then in the mid-90s, John Mather and his team started planning this, and I joined in 2001, 2002 with Rolf and Seth. We laid out what it would take to observe the most distant galaxies, see the very first stars form. But it literally took 27 years of designing, planning, building, testing, and so. And we had a few moments. It was not always easy for John.
Absolutely. And the last question is, what's next? These are obviously the first images. Are they going to be coming in like daily, weekly? And, where do you guys go from here?
Well, we're going to have images come in every day. Like, asking NASA for data is like taking a sip from a fire hydrant. This fire hydrant will be gushing and gushing for hopefully for 20 plus years. So it will be overwhelming. We will be flooded with data. I have guys like Jake and Seth here preparing the big database that starts today and tomorrow when they release our first. We'll be overwhelmed. We will be swimming with data. Literally. Well, ASU, of course, we have the School of Earth and Space Exploration that for many years has built on the prospects of exploring space, both with small rockets and from the ground with telescopes and balloons and with big missions like Hubble and Webb. So we've had this team at ASU in place since the early 2000s. People have come to us because they wanted to work on this project. And now more and more younger students and researchers who are going to work on this. And Arizona, the industry is important because local companies like Northrop is also in the valley, General Dynamics and Raytheon have been contributing hardware for this telescope. Of course, Northrop Grumman was the lead contractor. Raytheon has provided some of the mid-infrared detectors. University of Arizona also had its part building near-infrared camera detectors that were made in California. So a big collaboration we heard today between 27 states, but Arizona has been pretty much a center of thinking through how you would use this telescope at these near-infrared and mid-infrared wavelengths to see the first stars and galaxies, stars like the sun forming in these cosmic beachheads. So yeah, it's been 20 years of us preparing for this. It fits right in the school. The school here is about exploring space, exploring where we come from. We do this to find out where we come from. We are cosmic stardust, right? We're made out of these earlier stars that produced, the heavier elements that you see in the periodic system, such as calcium, magnesium, iron, carbon, nitrogen, oxygen, vitamins. They're made inside stars. It's only the hydrogen and helium is made in the Big Bang. Everything else comes from these massive stars, or stars like the sun, when at the end of their lifetime, they throw out their outer shells, which primarily consist of materials that then make future generation stars and planets. People. So yeah, it's the cosmic circle of life. Yeah, you're welcome. Yeah. Yeah, absolutely flabbergasted. I knew it would be good, but not quite as good. It was emotional. It was an emotional thing to see that for the first time. I saw the first release on Sunday morning, private WebEx, so that we knew what would be coming. And then, of course, we saw President Biden did beautiful. We could go back, Rick, to the cluster in the chest. I think it's, for me, one of the highlights. That's the kind of stuff that we wanted, right? Einstein would be so pleased to see that gravitational works so well, the one in the upper left. Not that one. Go back. Yeah, that one. We knew that we could use the gravity from the galaxy center You see all these objects in the background that are, almost like ringlets around the center, distorted gravitation by the gravitational bending, as Einstein predicted. So that to me was sort of stunning, jaw-dropping, stunning. How's that? Well, we hope we have, Rolf and others here are involved in these deep survey fields where we hope at a special spot in the sky where we can observe this almost continuously. We won't use the telescope, but we get a couple of times during the year that we observe this spot. We hope to see the very first galaxies, and on these clusters of galaxies, which we're also going to observe 7, we hope to see individual stars, very early universe, the very first billion years, that very rare alignments can magnify by many, many factors of thousands. We've observed this a few times with Hubble, but not at these great distances. We observed it sort of half the age of the universe back in time. And most recently, Hubble saw it, one star in the first billion years that would then suddenly along one of these arclets glow up because it was in such a lucky alignment that it was so highly magnified. We hope to see that a lot more. This is one of those rare things that gets a little easier further away. So we hope to get lucky here with Einstein's relativity. See more of those alignments, call them constant trends. Yeah. I was flabbergasted. I knew it would be good, but I had no idea. And yeah, absolutely not my socks. I was forward. Yeah. Well, the best Hubble images were also stunning, but they were, in a sense, limited in their color or wavelength. So their Hubble reaches a curtain, the wavelength slightly longer than 1 micron, 1.6 micron. A curtain drops. Hubble cannot look beyond that. And all the big secrets are in the wavelength range past that, rather than that. So our expectation with Webb, we're going to see into that first few hundred million years, see the first galaxy, first stars of the years. Well, it's like studying history. I think, Hubble looked sort of back into the Middle Ages, if you wish, Middle Ages of star formation, 1400s. Webb is going to be looking back all the way, maybe not quite to year 0, but the first few hundred years of history. That way, we're going to look much further back in time in terms of distance and expansion. That's a different relationship, but we're going to look several factors back in time of the cosmic expansion. That means we have to go that many factors rather in wavelength than Hubble just can't. Oh, I think we're going to have lots of great students and postdocs and researchers coming here to study this, and we're going to plan for the next mission. The NASA administrator was visiting here a month ago. We asked Rolf, I wasn't in town, what does it take to build next to Webb? The answer is, well, we have the technology in place. Rolf gave the right answer. We have the technology industry in place. We know how to do it. We want one much bigger. It will take manpower, human power, money, lots of time. These things take 20, 25 years to build. So this is what this is what we're doing. Right? Get the next generation out here to use the current data and learn how it's done, and then start thinking about what comes next. Yeah, so there were big dinosaurs on Earth years ago, they're no longer here. There were big monster black holes in the first billion years, and we have no idea how it got there. So they must have eaten Jupiter for lunch, Jupiter for dinner, and then Jupiter for breakfast for a billion years to grow to the masses they have, which is like 5 billion solar masses. So we're going to study some of the first black holes as well. That'd be probably one of the biggest things to find out. How could a black hole grow so large, so quickly? Please.
From Rosalia, who's in the research group, she's asking, especially regarding this kind of deep field image.
Yeah.
How far away do you think the furthest galaxies are in this image?
Well, we know for certain, we saw the spectrum, we have seen one at a redshift 8.5. That's mean the universe was 9.5 times smaller back there than it is today. And that's the first 586 million years after the beginning. So that's about 13.4 billion back years time. And that was, we looked at it quickly last week and saw that there will be many more. There will be more distance. I think we're going to go back to the first few hundred. How far back? We don't know. We don't know when the first star started. I think it is in the first 300. We don't know. And the further back you push, the harder it is. It's like the further back you push studying history, the harder it is to find the archives, the fossils, and whatever it is. So it will not be easy, but the telescope is built to see the very first galaxies, some of the first stars. Great question. Very good question. Be happy to answer more. And if I don't know the answer, there's a lot of folks here that work with us. Yeah, please.
Roger, just following on with your prediction of how deep JWST can see, how many hours in integration do you think it could see? It'll need to reach its limit of redshift.
Well, you've all walked probably at the East Coast at a night, saw the fireflies or Louisiana. You look at a firefly at the distance of Rick, it looks pretty bright. Take that firefly to the distance of the moon not there. We call that 31st magnitude astronomy. Firefly at the distance of the moon is what Webb can see 10 hours, 12 hours. And you've seen some. We certainly haven't pushed it to the limit. So Hubble in 841 orbits, 500 hours, 30, has reached just about that deep. But that took a whole month spread over many years. We hope to do that in 12 hours. We hope to go even fainter than that. But that will take some time and hard data processing. Have to get rid of all the systematic facts and artifacts and images you well know. That's not. Give us a little time. It will come. Hubble Ultra Deep will be redone with Webb. Webb will outdo it by large. Great question.
Technical question, sorry. There was a way that the Hubble Space Telescope 3 color images were mapped, and they call it the Hubble Palette.
Yeah.
Is there a Webb palette? Because now I know you're dealing way farther out into infrared. Has that been established, or is it kind of a work in progress?
Yeah, so there's various ways we can do that, and we're going to do this with our team also. So you can use blue for the shortest wavelength, green for the middle, and red for the longest. That's sort of like false core, what you expect. But if you look at some of these images we saw here with myriad emitting infrared elements, there's a lot of molecules like hydrogen molecule, carbon monoxide, and other molecules, nitrogen, silicon, that shine at specific wavelengths that we'd like to image and then render in a certain color. Say, well, red is the reddest of those lines, atomic lines or molecular lines, and green is the middle, and blue is the one most shortest wavelength. Then you get to see the spectacular contrast between those different molecules. That will give you a sense of where the elements are produced and how they're expanded. Like, for instance, Nebula, the one in Karina. Yeah, the cube. Southern ring then, not the constellation. Great question. So yes, we will do some of that, but we will do it more along the atomic and molecular structure you see along the rainbow palette. Other question? No. No, if we were allowed to name it after our children or neighbors, we would be rich by now. But they have telephone numbers, long serial numbers in our catalog. We're not allowed to name it. You know, if they move and they're planets, we can name it. We hope to occasionally find some foreground stars. Like for instance, the field that Wolf will be studying there, you can see things, piety, flip, move, name. Not these, they have just serial numbers. Well, that's a big deal. We run at 28 gigahertz Ka band, where the data comes down pretty much 24 hours a day, 8 hours in Australia, in Canberra, 8 hours in Quilspa in Spain near Madrid, and 8 hours in Goldstone, California. And all these radio telescopes bring the data down Maryland. And you know, any of the images, Seth, how big are they? Many gigabytes, right? 10 gigabytes. And that's just a single image, 100-second exposure. And we'll get that 100 times a day or more. So we will have many terabytes a day. Overwhelmed. Cannot buy disks big enough to store it. So, yeah. Well, we'll be sitting behind computer screens a lot and downloading data and then try to process it. We have a whole pipeline in place to get rid of all the incidental effects and carefully align these. These images would never look this good if you don't get the blue and the green and the red right on top. So you have to very carefully register. You have to remove all the incidental effects. The space is an unfriendly environment. A lot of cosmic rays, protons coming from the sun that hit your detector and cause blemishes that you don't see here, but they need to be removed. So all these folks here, they're going to, you know, remove these artifacts. Make sure these images are properly qualified. That's quite a. Yeah. Well, because we've been involved, I've been involved as interdisciplinary scientist for this telescope, meaning that I had to help NASA define what it needed to look like in terms of science and the requirements. How good is the resolution, the wavelength, stability. And so in exchange for that, they gave us 110 hours of observing. And that is happening right now. First couple of hours was taken last. And over the next year and a half, the other 5 or so hours taken on maybe as many as 15 targets. Some of them get observed multiple times at different. So we get a really good feeling of books. We'll be able to find variable objects like Joe Stephan's quintet, the 5 galaxies. One of the galaxy with a very bright, that one. This galaxy on top, if you look at it in the mid-infrared, I don't know whether the mid-infrared image is fine. It looked like a bright star. It is not a star, it's a black hole with a very bright accretion matter falling in that causes enormous radiation of all wavelengths that comes out. But it's a very small object that's very bright. And there we hope to, objects like that, to find what feeds these black holes, how rapidly, and they don't they don't shine steadily in time. They fluctuate up and down because matter keeps falling in the black hole irregular, but they eat the Jupiter for breakfast. thinner for 1 billion years in a row, and that causes the brightness to fluctuate. We hope to see that too. Yeah. Well, what would you say, Rolf? The North Ecliptic Pole field, where we hope to observe many times in some of our galaxy clusters. Get the galaxy cluster observed next month, and we already had 2 targets observed. One was a protocluster at redshift 4 when the universe was a few billion years old, but we hope to learn how these galaxies start agglomerating and growing, feeding the black holes. So that's certainly one. We also have a set of overlapping galaxies where one is in front of the other. We saw many examples already today where one bright object in the foreground partially blocks the light background. You know what the background object looks like. Find out how much dust this galaxy has in the foreground. That tells you then how much material it is, out of which form new stars like the sun, like Earth. Oh yeah. It's mind-blowing. The image quality is so good. Look at that star. They're perfect Christmas stars. All of them are perfect asterisks. And that's because the mirror is so good. The mirror is polished far better than we had hoped for. It's aligned far better than hoped for. It was supposed to be, total surface accuracy of 50 nanometers. It's more than twice as good. Of course, it will slowly degrade over time. Occasional micrometeorite hits, occasional some dust or cosmic material will settle on. So it won't stay perfect forever. Mirror is much better form than we had hoped. Oh yeah. Yeah, so there is, well, certainly we'll look at the black hole area near the galactic center, which was the Nobel Prize winning topic of last year. And stellar motions around that black hole will tell you how massive it is. Certainly going to image that again at high resolution, big spectra of these stars, so how fast they move. But also nearby planets, stars, exoplanets will be observed either directly by putting like a cold finger on top of the star, so the starlight gets blocked. See, or the coronagraph. See the planet right next to it, or like where a planet goes in front of a star and partially blocks the starlight with its atoms. During that time, which is not very long, you can observe the color rainbow spectrum of that planet's atoms, find out what it is, water or oxygen, carbon dioxide, even ozone. That will be like jackpot of kind of materials, building blocks. Yeah, these are great questions. Be happy to take some more. Well, we could certainly put a more educated presentation together on what we've seen today. It's not that it wasn't good, but it was very quick and we didn't look at all the details that in presentations folks here can talk about. When our images come in at first, they may not look the way you expect. So we have to process them, calibrate them, find them, make them look like color image. But we certainly hope that some of our first targets will have papers ready to go to press in months, then present in the media as well. There's a timing involved. Sometimes the journal will not let you run to press before the paper is accepted. You've got to be a little conscious. So great questions. Other questions? Yeah. Yeah, that will happen. We can't really predict that. Well, certainly this image will, wherever the cluster of galaxies. But I want to give my people the chance to answer that too. How do they think their career will be changing? The career, they will work in astronomy, but they might focus on different science topics based on what these images tell us. That in the outskirts of these images, if you turned all the lights off, you can see some very red objects, and those are the ones at the largest distance. I expect probably change the research focus. Do you want to answer that, Paul, Seth, Tim, or Jake, or Darby? Go ahead. Yeah, go. You guys can come up too if you want to.
Sure. So many of our targets serve multiple purposes. So we expect to see, we take a particular target because there's something in the center, but the field of view of this telescope and of the instruments on this telescope are large enough, are wide enough that in many cases we see objects outside of that target area. In other cases, we see objects also in the foreground and in the background of the actual target. For instance, one of the fields that I'm particularly interested in is in the north ecliptic pole area in the sky. And we look not just at distant galaxies there, we also look through our own galaxy to get out there. And in fact, we look through the outer parts of our own solar system near the ecliptic pole, so out of the plane of our own solar system. And what you might expect then is if you repeat visit these areas in the sky, that you might see, say, comets coming in way out from the Oort cloud. And we already would be able to see them near the orbit of or the equivalent of the orbit of Neptune. Then we look through our own galaxy, quite a long sideline through our own galaxy where we see faint stars. We can see stars move because the distances are small enough and the resolution of the Webb Space Telescope is fine enough that we would see them slightly move over time. And then there is nearby galaxies or relatively nearby galaxies, intermediate redshift galaxies, or galaxies that we see as they were several billion years ago. And then hopefully we see these rare objects that bring us right back to the very, very first objects that started to shine in the universe.
Laser.
Right. So one of the things, is it upside down?
Yeah, it's
this one? Yes, okay, here we go. So for instance, there is this little red speck that's visible here. And some of our colleagues, they put together a comparison of prior images that were taken by the Hubble Space Telescope of this area in the sky. And this particular galaxy was not there in the Hubble images. And it's quite bright here. So we look at a wavelength range that was to which Hubble was blind, which corresponds to a distance that Hubble could not reach for an object of this intrinsic brightness. Like one of the things with Hubble is that it's great at detecting ultraviolet emission, even from these very distant galaxies. But these distant galaxies might not have been very bright in ultraviolet. They may be bright in their optical, visible light. And that light gets stretched to wavelengths that we now observe in the infrared. And that's why this one pops up in the Webb image. Similarly, there's throughout this field, actually, you will not be able to see it here because it's, I think, off the bottom. There was a nice pair of galaxies that are very, very red that just popped in and out if you compare it between the Hubble image and, oh yeah, here we go. This pair of galaxies is very, very faint in the Hubble image, but it sort of pops out in the Webb image. The fact that you have these lensed galaxies where this galaxy is actually an image, this galaxy is an image of the same intrinsic background object. It's imaged twice because the light got bent in such a way around this foreground cluster that you see it twice. And then there's many of these arcs where, in fact, you see two arcs that are images of the same object in the background. So these kind of things are the low-hanging fruit right now, the things that immediately catch our attention that we're really excited about. But of course, there's many, many questions that we don't quite know yet how to ask. And by observing images like this, we will get to those new questions. And all the students, the young students that just are starting their careers now, they will make a career out of those questions. Wait. Yeah, that is both a difficult and an easy question, but there's so many different metrics that you can use to answer that question. Like sometimes you are looking for something that is intrinsically very small, and in that case, resolution might be your key metric. In which case, Webb is just flabbergasting. It's great how fine a detail you can see with this telescope. It can see as fine or better as Hubble can at wavelengths that are longer, and usually, if your wavelengths get longer, your resolution goes down for a given size telescope. Since we're in space, we don't have to worry about the disturbing effects of our own atmosphere. Even though you can have a bigger telescope on the ground, you have to look through that atmosphere, and it's quite hard to correct for that, and you can only partially correct for that. In other cases, it's the atmosphere itself is shining at these long wavelengths. So even if you have a big telescope, it's like looking through fluorescent lights or through lights to get to the objects that you're interested in. If you're in space, you don't have to worry about that. It's dark. So you can actually see these faint objects that you would be blind to even with very, very big telescopes on the Earth. In other cases, it's that the particular light that you're interested in corresponds to an absorption feature of a molecule in our own atmosphere. So that light never makes it to us to begin with. In space, you don't have to worry about that. The other thing, let's see, what other metrics can we come up with? Just the sheer size of a mirror that is cooled to these cryogenic temperatures in space, that therefore does not glow itself either. Whereas a telescope on the ground is per definition about room temperature, plus or minus 20 degrees or so. That mirror might emit more light of the kind that you're interested in than the objects that you're interested in. Therefore, you would not see them. Whereas in space, with these extremely cold temperatures, the telescope is nice and dark, doesn't glow too much, and you can pick up these faint objects. Seth, did I miss? That's pretty good. So hopefully that answers your question, but it depends what you're interested in. What is your key metric? Yes, R-O-L-F. That's my first name, Rolf. Janssen, J-A-N-S-E-N. And I'm a research scientist here in the School of Earth and Space Exploration.
And so in space, the sky is at these wavelengths 10,000 times darker than it is from the ground. That turns Hubble to a 64-meter ground-based telescope for certain applications, and Webb, what 150 or 200 meters calculate. Something we can't build on. But what the ground can do, I'll be honest about it, because the telescopes are larger with what they call active optics or adaptive optics. They can pick a star, make it very hot. So something that's bright, much brighter than the background, they can observe it at higher resolution than Webb or Hubble. But it's only over a very narrow field, and you'd be hard pressed to see something faint around that star, like a planet or a disk or something. So the two are complementary in the sense that sky will always be darker for Hubble and even darker still for Webb, and that's why we can see that firefly. You won't see that from the ground. So, but the ground can, for special purposes, bright objects can get very high resolution. And the other thing the ground can do is when it takes these rainbow spectra, it can do hundreds of thousands of colors. Well, with Webb, we get what, 5,000. So we don't have as many colors. We have enough to do what we want to do, but the ground will have higher, what we call spectral resolution, just more colors, because you can sit on a target and look at it forever. Therefore, split the light up in many more wavelengths than Webb.
Yeah, and the other thing is that from the ground, you can have a rapid development cycle of new instrumentation and new modes of observation. And only once you figured out how to do it, would you put such an instrument on a space telescope. You don't figure out those things typically on a space telescope first.
That's right, yeah, exactly. So the two are complementary. We think of the Hubble and James Webb telescopes that over a relatively wide field look at very high resolution, very dark skies. The ground will come in heavy bombers which that collect much more photons and split them more colors. Look at very bright high. Ground can complement it. For instance, when we find an object, well, an interesting object at a large redshift ground, look at certain wavelengths, study its velocity, fast approach. Great question.
Sure, we're past the time allotted for
yeah.
the questions and answers and
Right.
whatnot. But we want to thank you guys for being here this morning and helping us just sort of see these first images together and understand some of the significance. I think it's amazing. I love the idea that you're just pointing out galaxies that just last week just sort of popped into existence, things we couldn't see before. And there will be thousands, not there millions. All right. Well, thank you very much, everybody. Thanks for coming.
Well, thank you for organizing this. It was great. Yeah, thanks, Tim. Thank you, folks, for showing up.